to sign down a little bit.
Mute everybody. Wolfgang, you'll have to unmute yourself and we're off.
Okay.
So can you share your screen?
Share screen is here.
There we are.
Screen.
Yeah.
Share.
Brilliant.
Okay, now to make this the show. And do you see it?
Yeah.
I think you see all this, okay?
Yeah, that's great.
All right.
Great, great.
So physics in the first person observer framework. So I am going to present a fairly upside down or different view of physics and science that I hope will inspire all of you to join a new approach. And the problem is that for centuries, so I'm going to read a lot of this stuff, but then try to also be a little spontaneous. For centuries, the strategy of science in general, and physics in specific, was to attempt to discover the laws of the universe first, and then explain how conscious living beings emerge from this dead material. I am reversing this approach and propose that we should build theories of conscious beings first, and then explain how such beings incorporate the concepts, models, with which they explain their own experiences. My intention is to expand physics to include the systems that actually invented it. My approach assumes the first law of physics should be that the physicist built the law. I will therefore introduce first a model of the observer, then explain how observer effects can be falsely attributed in our current science to an external world, using special relativity as an example, and then open the discussion to the question of how understanding observer effects can simplify current physics and open the door to a large number of new phenomena. Now, it's very important for me to emphasize that I'm not proposing a negation of our scientific discoveries. Facts are facts, experiments are experiments. However, I am going to propose a formulation of science that is simpler and will allow us to incorporate new phenomena because the correct role of the observer has been included. Now we begin by examining the nature of the ordinary here and now experienced by all human beings. This here and now was first drawn by Ernest Mach. You can see his nose on the side here. This is just a general room, so we're looking out of the left eye. It was then updated by J.J. Gibson in the 1950s and further updated in my PhD thesis to include a book. This is this thing right here. This book externalizes any model of reality and adds to the original drawings by Ernest Mach a place for all symbols to be identified and located. This is very important because without this, All we have is the direct experiences. We need the book in order to allow us to have a place for our symbolic logic, theories, and other ways of understanding what is going on. Now, there are two fundamental interpretations of what the first person experience actually is. The first one is shown here, and it is what we call the Aristotelian interpretation, which professes that we see the real objective world. In other words, this thing is the real objective world out there through the window, this is a window, of our senses. According to Aristotle, this world of objects exists whether we look at it or not. And it is the challenge of natural philosophy to discover the properties of these objects, including our own body and, all the other things that are out there. And Aristotle's approach forms the backbone of classical physics and remains the guiding principle of Western societies and dominates practical behavior, no matter what else they think, the practical behavior of almost all of the world's population. Now, appropriately for this group, the alternative natural philosophy, interpretation of the here and now, comes to us from Plato's cave analogy. Plato assumed we are like prisoners in a cave who are shackled to see only the projections of shadows from an external world. Here is a projector. Here is the input from sensory stimulation. And Plato assumed that somehow we were projecting in front of us the shadows of an external world, a real, he called, ideal world. And it's in order to make this ideal world accessible that I introduced this book, which represents all of the symbolic theories and writings that are available in our society. In modern terms, this means we are the little men and women inside our skulls. So we, meaning prisoners in Plato's caves, are out here looking at projections from external stimulation. This first-person perspective space is often called by other names, such as the third eye, Hesse's Magic Theater, or Barr's workspace. By adding a book, I propose that these prisoners in our skull are working to build a memory model of their concept of what the real outside world of the cave is like. This model of reality is here shown as just symbols, and this is just a headline name, effectively, of all this stuff. This model of reality is shown as symbols coded into books, most usually written in the language of mathematics. But of course, the philosophers do a lot of talking and logic and so on and so forth, but mathematics is the main language. Now, rather than a single objective world, we are now confronted with a new cosmology of many individual caves in which many individual concepts of reality are formulated to explain a world of mutual interactions. In other words, the cosmology here is a kind of multiverse organized into communities of symbolic communication that have developed a consensus reality of understanding whose only criteria is success in fulfilling its desire, which I am proposing involves two aspects. One, the desire to grow, and the second, the desire to minimize internal forces of stress and strain in our own selves. Now we'll see that the world is largely divided into two groups. One group emphasizes growth, the other group emphasizes the comfort that we all like. And I think both of them are equally important. Now this page is not absolutely necessary, but what I'm trying to show is that the book here and all its pages represent all of the books we have in our library, and many of them contain some simple relationships between sensations that we can see and the symbology with which we deal with those sensations. So here, for example, we have an exact snapshot of what happened to me when I threw up an apple back in 1971 when I was doing these experiments. And what we see is that we have in our symbology the name of an object. We have some parameters such as it's 1/10 of a kilogram. And in this particular case, I've captured it just as the vertical velocity is 0 at the apogee of this object's trajectory. So in other words, we've divided our experience here into what we see directly, which is out there, and how we transfer that direct seeing into the symbols with which we capture our knowledge of what we cannot see directly. Now, any model of reality we can construct must be placed within the context of its use to explain and control our interactions with the external reality. This reality is the Kantian unknowable, or I would say it's also Anton's fallibilism, because it can never be seen directly, even in principle, because we can never get outside of our larger selves, the cave. All models must therefore fit within the activity of explaining and controlling our sensations. These are here shown as an apple. And what I've done is said that there is a motion here that I have made into a model. The real motion is from the sensations we experience out into ourselves, which are then processed through our arm into a model, which in turn is read again to produce control signals for the sensations that we experience in our lives. So these two arrows represent the activity of taking sensations, qualia, if you have that term in your head, into a model, which in turn is then produced and placed back into control of those sensations that we experience. And this here represents the externalization, model externalization of something that we first-person individuals actually do. Expanding that now is a simplified model of our general mental processing activity. Included here are the external interactions, one, from our sensors which we cannot see or experience. You simply do not know and you do not see the photons hitting your retina. All you see is the result. So this stuff out here is processed into the area in our brains or wherever they are that we see the sensations. Here is the output to a black hole, which is where the activities and action goes, and we don't see the results until it comes back around like this. Now, the internal model of what we do is shown in these areas. First, the sensations are compared with an expectation that our model of reality generates. They're differenced, and the update signal here, number 4, changes the model. The model itself then can be looked at from 2 directions. One is if we look at it from this side, we will see the output of the expected sensations we see that are compared with the incoming measurement sensations. And this then becomes a loop that is locked into our measurements. So our measurement is this from the external world. This here is the locked loop. And we know that when the model of reality generates the correct and equal sensations, that there's something correct about the model. The model itself, however, can be looked at from a third-person point of view, and that generates a second loop inside, which is a meaning loop. And that's the one that generates our meaning out of our memory. And instead of going further on, now this is a model that's been extensively presented and explained in my book, Conscious Action Theory. So I'm here going to go on and immediately, I could talk a lot about this and probably should at some point, but I'm going to go on and simply present the architecture of this action flow as the model of our conscious being. Now, in this slide, I want to draw your attention to the central oval in the first person's. This is what you actually experience. Okay. This is the first person display, and it's shown in a thought bubble here. So this part here, you can see there's a little nose. There's the apple that you see as a first person experience. It's enclosed in a thought bubble, and it's connected normally in a cartoon set of bubbles to an output from what we believe the real world is. Therefore, in an everyday operational configuration, the explanatory sensory experience, which is this one here, this shows an example or a picture of a classic objective world, basically a space with stars, an earth, a sun, the first person individual's body, and something that he's holding. So this is the explanatory sensation that is produced from our memory update. This here is the loop that's locked basically into our input and output system. And under normal circumstances, the sensations and the memory explanatory sensations are fused together, and that fusion very rapidly takes less than 1/10 of a second to take the sensations, explain them through the system, and then what you actually see is an explained set of sensations, which we call an object. And it's that combination that produces the world we believe to exist in. Now, I propose that this objective world, which is a fusion of the sensations and their explanation sensation, that this objective world that we live in, the thing in front of us, the thing in front of our noses that we feel to be surrounded by, has always been a personal, internal phenomena embedded in an action flow architecture, a bigger system here, action flow architecture. and the physics describing what the observer actually does to see and act provides the context for any model of reality which we can come up with and which each of us individually champion to, and that championship includes all of contemporary physics. Now at this point, I want to go just one small step further and say that in order to get a little bit more accurate in what the model of reality should include, we can see here that it involves being in two basic cycles. One here is the cycle that represents the potential lock to the external world. And when that individual is isolated, an isolated conscious being who has no input and output, then this runs as an open loop. And what's left over is simply the memory loop. And this combination, which now contains the substance from which the memory is built, being processed into the sensations, which we'll call the fields, which then regenerates the substance, the memory, is the essential model of what I believe that we bigger individuals are. In other words, what I've done here is to emphasize the activity through which we generate our sensations as being more fundamental than any of the sensations or any of the experiences that we actually see. Now, for you guys that are mathematicians, what I'm saying is that the model of reality is not going to be the actual symbols that you write on a page. The actual model of reality is the activity of writing those symbols, because those symbols are in a larger system and they are not the things in themselves. They're merely the phase of the activity that we actually are. Okay, that sort of want to summarize the presentation of the model of the observable and the fundamental principles that I've presented here in my book, Conscious Action Theory, which are that the first law of physics should be that the physicist made the law, that we should build a model of the observer first, and then find the best model of reality that the observer can build. Doesn't do any good to just come up with abstracts. You have to figure out, or the best we can do is a theory that we can actually create. And best in this context is something which is the most useful to achieve our goals. Now, to continue, I've stated what are the goals. And there are two of them. All systems want to experience more action. They want to grow. Secondly, all systems want to experience the actions in the form of minimum force. This basically says that all systems will conform to the minimum action principle, and yet it has interactions where its basic desire is to adopt and absorb more activity in its own structure. The last statement here is that all systems are actually observers. In other words, all of physics can be reformulated so that all systems, rather than being out there, are actually acting like observers that absorb and that behave as though they want to satisfy these two goals simultaneously. So that now concludes the first part in the presentation of the observer model that I believe needs to be developed first in order to show what physics is like. The next part is going to be a little more technical, and for those of you who aren't physicists, this is a problem having to do with general relativity and special relativity. What I'm going to do is to present special relativity and the thought experiments that led to its Lorentz transformation and adoption for physics in general. And the problem that is addressed in special relativity is that that we have two coordinate frames, each making measurements on an event and producing a position and time variable, two of them. And the question is, what is the transformation between these two? Because we have assumed that the event only happens in one place at one time. But when we measure it with two coordinate frames, we find that we get two numbers or two sets of numbers. The question is, how do they relate? So that relation is a transformation between two measurements. Now, what I'm doing here is we're going to be using the first person perspective. This thing here is the first person perspective in order to see how the observer is actually involved in generating these theories. Okay, so in addition to the two objective observers and the experimental apparatus within which they're riding, I believe it is an empirical and demonstrable fact that there is always a third person observer executing thought experiments leading to the special relativity theory. And not only that, but there's always a background observer, so that the entire question of whether or not there is an ether or not should be cast within the context of the fact that the observer, the person who creates the theory, is always there and can't be eliminated. And in this case, excuse me, what I've done is, excuse me for a second, I got to get rid of a cat that's constantly. All right. I've got a bunch of cats that always love to get involved. Okay, so that the first person observer always provides a perspective within which all of the thought experiments are performed, and it can't be eliminated, so that effectively something like an ether is always there and it should be identified with the first person. What this does is gives us three coordinates or coordinate systems. One is the xt coordinate frame, one is the x prime t prime coordinate frame, and it introduces a third one which I'm using capital X and capital Y and capital T. Okay, now we are not taking the Aristotelian point of view. We are taking the more Platonic point of view, so that these items here are to be considered to be projections from sensor experience or internal, and we are looking at them as are the prisoners in Plato's cave. So we're always inside our skull looking at these projections. Okay. So now let's look at using Einstein's postulates to build a coordinate frame. And our general plan now is going to be to ask the question, how does Einstein produce and build a coordinate frame? And he proposes that there are two basic postulates. One, that the speed of light is constant for all observers, and two, that all observers are moving with a constant velocity, which are equal. Well, all observers moving with constant velocities are to be treated as equal. Okay. Now, Einstein's postulates to build a coordinate frame, therefore, in our approach now gives us three coordinate systems within which to look at the experiment. In this particular case, the third person observer axis that I've introduced, time here now moves directly through and perpendicular to the space of the screen within which or from which you are watching. So time here for this observer moves directly, I don't know how to exactly show this, but directly through your eyes, right? What that means is that this entire space here happens at once to you, the third person, the third observer in the system. Okay. Now we're going to show that we will build and synchronize each observer's coordinate frame according to these postulates. And what we will show is that mistakes will be made. And those mistakes will have to be corrected. And this provides a tautology in which the construction of our coordinate systems introduce errors that have to be corrected by always applying the Lorentz transformations. In other words, we make two errors that cancel each other, and that's the essence of special relativity. In order to carry out that program now, I'm going to try to construct a coordinate frame, synchronize it, and show where the errors come from and why Lorentz transformations are necessary to correct them. Okay, the first thing we need are real physical units. The basic unit from which, these are real physical things. The basic unit from which any space-time coordinate frame can be built in the abstract is an action detector attached to a clock. This is a system which in our objective frame of mind has got three spatial coordinates, distances, dimensions, and an intrinsic parameter which is convenient labeled the o'clock parameter or time, which is the state of the system, engraved on the clock dial. So here's a clock dial, it's engraved. And we read off the instantaneous state of the system by the position of the pointer. So there is a unit, it's a physical thing, and we're calling it the unit from which measurement of space-time system can be built. All right, now this is a fairly complex slide and I have to probably take some time to explain it. Here over here, what I've got is a model of the observer. In order to run that model, action flows through these architectural paths. And what I've done now is assume that along this timeline, which is the timeline of the observer, we are actually executing these activities presented by the model. In other words, This is a snapshot at one time t. The interval between getting from here to here, the third person is executing activities, and we take another snapshot here. We take another snapshot here. The activities he is executing means he's sending out a signal into the unknowable. He receives a signal from the unknowable, and he generates a rationalization process that allows him to not only present the here and now, but present his explanation. This set has now been expanded so that we see it from a straight front point of view. And in this thought experiment, what the first or the third person sees is the stationary clock moving on this trajectory, which is parallel to the observer's trajectory, the third observer's trajectory, and a moving clock, which moves in this direction and in the spatial direction in the third person observer. Okay, now the third person observer, we will notice, is moving now at a slightly longer distance. In order for this clock to execute two things, one, to execute the activity required to move the pointer forward and therefore change the state of the clock. The second is it has to move through a distance in space so that two activities are involved. However, the moving clock on its own executes the same activity, since it's the same clock as the stationary one. It executes the same activity in an equal amount of action. Action is therefore the central invariant. In order for a clock to both move in space and move in time, more action is required, and therefore the speed, the apparent speed with which the pointer moves will slow down. Okay, the actual calculations are typical of special relativity calculations, and what we see here on the right-hand side is the observer, third observer's activity on a vertical. I've got now two clocks moving, one at an angle alpha, the second one moving at an alpha plus theta, or theta relative to each other. And the projection of the rate at which the pointer moves onto the third observer, you can see, is geometrically shown here, right? So that the clock moving in this direction is projected to this space. The clock moving in this direction is projected to this space, and the observer himself is moving along this line. What is important, very important, that I'd like to emphasize is that the speed with which all of this happens is the speed with which activity happens in the observer, the third observer who's looking at all this stuff. In other words, the speed with which you guys out there, the audience that I'm calling the big we, is moving through time. Okay? It is not the speed of light. It is the speed of activity in the observer and in the material of the observer. So the speed of light is not a constant. The speed of light depends upon the gravitational potential in which the material in which light propagates is determined. And we'll go into that a little bit later. Now, the geometry of this activity, if you notice here, effectively one can consider this to be an action moving along a trajectory. The geometry is shown here on the left-hand page. We can work through it, but in order to make these calculations, whether or not it's one clock projected on a second clock or both of these clocks projected on the main observer. The calculations go through, and what we find out is that every clock appears to be moving in slower in every other clock's coordinate frame by a gamma, which is 1 over 1 minus v squared over c squared, square root, the normal gamma function, and it depends on the alpha and theta angle with which the clock time in the third observer is then projected on it. What this means is that well, I'll go to the next one. Okay. So mapping the timelines around, instead of in straight lines, mapping them around clock dials, we can see that the time of a moving clock will always be slower than that of the system within which the clocks are displayed by this gamma factor. And the gamma factor depends upon the velocity, the relative velocities. So the clock here moves a little slower.
Careful.
The clock that even got a higher speed moves slower still, and so on. So this is a general statement that moving clocks in each observer's display space appears to move slowly. Okay, now we've got a physical description of the element or the unit with which a coordinate frame can be built. And at this point, we've defined the physical clock detector unit. Now, I'm always talking in terms of real things here. So this is not just a symbol, but this is what appears to be a real unit. So a physical clock detector unit can be used to build a coordinate frame. So we're going to do that. We're going to build a coordinate frame, and it's fairly straightforward. To do so, we physically place clock detector units end on end, sequentially building an x-axis, and we're going to label each one of these clocks by numerical values. So here's 1, 2, 3, 4. So we're all labeled. And the distances are the label times the unit length. So for example, here, this clock is a distance 4 units away from the origin. 1, 2, 3, 4. So, right. Okay, so this is how the x-axis is built. Now, you will notice that if there is a displacement error in building these coordinates, for example, if the event here touches just the -3 labeled clock right there at the end, but there's a little error having been produced in the construction here, then this system with the error will report a -3 UX distance for when this activity happened. But if the gap were closed and it were constructed correctly, that same event would actually be reported to be at -4 times the unit. Therefore, construction errors of how to build these things will show up in errors in reporting. Now, here comes the main point of this portion of the presentation, or the reading. When building a coordinate frame, according to special relativity instructions or protocol, systematic displacement errors will occur. And to correct these errors, Lorentz transformations must be applied to the measurement results. So what I'm saying is that any errors that we make in constructing the coordinate system can be corrected, but the combination of the two is actually looked at as an introduction of an error in building, which then is corrected by applying a specific formula to the measurement results from the incorrectly constructed coordinate frame. And that's to show how this now happens in the special relativity procedure for setting all of the clocks from the stationary, for a stationary unit, we measure the round trip time and multiply it. So how that happens is you send a signal out. This is stationary system. You send a signal out, you get a reflection back from each of the clocks. You measure the round trip time, and you set the distances to the half the round trip time multiplied by the speed of light. Okay. And when you do that from a third person point of view here, this is us looking at it, all the clocks will simultaneously have their pointers looking at the same place. So this system now has been synchronized using a clock pulse, synchronization pulse. And when the synchronization pulse arrives at a clock, that clock is identified as being at half the speed of light times the round trip time that it goes. Okay, so here at the bottom we see that the offset that each clock is set when the synchronization pulse arrives is simply the time of when it left plus the name of the clock divided by the speed of light. Okay, now for some reason, there we go. Okay, so using the exact same procedure, we build and synchronize a second frame, which then is placed next to the first frame. So now we have two frames, and all of them, when synchronized, are telling the same time. They're stationary relative to each other. They're stationary relative to the third observer that's always in the background. And an event that happens will now produce two timation signals, the position and the time at which an action happened at the receiver here. And these two numbers will always be the same because everything has been constructed with exactly the same construction rules. Okay, now we accelerate the T prime frame to a velocity V, and we maneuver it around a big cycle so it comes parallel to the original stationary one. And parallel to the stationary frame, this will allow the moving frame to synchronize its origin clock and then resynchronize the rest of the clocks while moving at constant velocity relative to the stationary frame. So let's start this procedure. Here it is. The moving frame has come around. It's now at the place where it's just the origins of the two clocks are just parallel to each other. And at this point, a synchronization pulse is sent out. Okay. Now here, the stationary T observer, this guy here, is not moving relative to the background space, The T prime coordinate is moving relative to the background space. However, because of Einstein's protocol, the moving observer thinks that the speed of light is moving at c in his coordinate frame, and the stationary observer thinks the same thing, but the moving observer is actually making a mistake because the speed of light is determined by the third observer who provides this background space. So there's a mistake being done, and this is the reason a second systematic error will be introduced when building a coordinate frame. Now, the next sequence of slides shows me how this works when overall. And you can see that at time t1, now you, the third observer who's looking down on all this stuff, will have these t times, and these are all the clocks. And here's some events that take place. Okay, so at t1, the pulse has arrived now at a typical clock, and that clock has been offset by x1 divided by c. In other words, the name of this clock divided by the speed of light, because that's the distance. Because the moving observer, however, you can see in his coordinate frame, the speed of light relative to his coordinate frame is actually c minus v. Okay. Now, the next step is the pulse arrives at the clock of the moving observer. Now, the moving observer thinks, because he doesn't feel any forces on him, and because Einstein has said that he's the same as the stationary observer, he sets his clock to the origin send time t prime plus the distance divided by c. In other words, when the clock pulse arrives, he will set his clock pointer offset by this formula, which is the distance divided by c. This means that there's a mistake. The mistake is made that one, the clocks have moved more slowly with a gamma factor, and two, the clocks are not at the same, at the distance he thinks he's calculated, because rather than dividing by c, which is the protocol, he should have been divided by c minus v, which is the actual speed relative to his coordinate frame. In other words, two mistakes have been made. Okay, now just to finish off, the pulse comes back. The pulse now is at T4, arrives at the origin of the moving frame, and then eventually the pulse arrives at the origin of the stationary frame. And what you can see now is that from the third person's point of view, each of these times happen at different times, whereas the moving observer thinks they all happen at the same time. So a mistake has been made. Now, Einstein's procedure for setting all of the clock is simply what I've just mentioned for a single clock, where it all happens at once. The moving observer sends out a pulse. There's a reflection from each one of them, and when that pulse arrives at each one of the clocks, the moving observer, because he believes that he is identical with the stationary observer, always sets the offsets on his clocks at the distance divided by c, when in fact it should be divided by the distance divided by c plus or minus v. So he's making mistakes everywhere, and therefore when the third person observer looking down from a God's eye point of view looks at this result, he will see that the clocks are not synchronized. They're all at different places, the pointer positions. Okay, so Einstein's procedure produces errors. You send a signal, you get the reflection back, you calculate it out, and what happens is that the first error that's introduced is that the times should all be, instead of simply be t, they should be divided by or multiplied by the gamma function, 1 minus v squared over c squared. This shouldn't be 2, this should be up. And the clock positions are all off by the same factor. To summarize, the stationary clock, whose name is x, whose actual distance from the origin is in fact x, the same as its name, the time when set to t is actually t. The moving clock, when synchronized according to the special relativity protocol, the clock whose name is x is actually at x divided by, or multiplied by the gamma factor, divided by 1 minus v squared over c squared square root. The synchronized clock is set to t, but it actually should be set to this. Again, the gamma factor is in there. So applying the special relativity protocol to synchronize moving coordinate frames introduces two systematic space-time errors. Okay, so we can correct this error by adopting a new protocol when building the space-time coordinate frames, or the alternative is, in physics, it is led to the rule that all acceptable theories must be Lorentz invariants. In other words, include correction transforms. All right. Now that we've understood that there are two types of errors introduced in the construction of coordinate frames according to Einstein's protocol, the question is, why does this lead to the Lorentz transformations? And in order to calculate that out, we have here now the original problem, which is that we have a coordinate frame which is stationary, where all the clocks are showing from a third observer's point of view, are all synchronized. We have a second clock which has been falsely synchronized, and we can see that the times all differ out there. And of course, it's obvious that one coordinate frame shows an xt, another coordinate frame shows a different result, and we have to rationalize these two. Now, the calculation for doing that was actually presented on Carter Mead's Collective Electromagnetics in the notes from this slideshow. It goes through the direct calculation, but the process begins by recognizing that this is very important. The name of the moving clock, in other words, the moving clock, both clocks do the same thing. The name of the clock is now its address in the coordinate frame. So X, Y, Z. It's the name of the clock. It's been etched into the clock. It's been placed into the RAM memory of the clock system that generates its timation, or its measurement signal. That name does not change when the coordinate frame is accelerated to another velocity. Therefore, every one of these clocks will report its point of position and the name at which it has been identified. And that's the X prime T prime that gets reported. That report will be false because the position of the clock is no longer at X, it's at X times gamma. And the position of the clock pointer is no longer at T down here, but at T times gamma. As a result, we have, I don't know why this is up here, but we have proven the following. By constructing by constructing the synchronization of two coordinate frames which are moving with constant, oops, sorry. How does that happen? No, I don't know what the heck has gone on here, but okay, come on. Okay, there we are. All right. By constructing coordinate frames that are moving with constant velocity relative to each other, according to Einstein's assumptions, and these assumptions are: one, the speed of light is the same constant, 3 × 10⁻⁸ meters per second in all inertial frames. And the second assumption is that all inertial frames are equivalent and there is no preference. Now what we have done is identified two systematic construction synchronization errors, which will cause space-time measurements of a common event to be recorded as two different xt and x prime t space-time values when one of the frame is moving relative to each other. In order to eliminate these differences, we must apply the Lorentz transformation between the two coordinate frames, and here's what they are. If the coordinate frames had been constructed to account for the fact that the speed of light is constant in each observer's material, then the complexity and non-intuitive aspects of special relativity could be avoided. And that now is the end of my official presentation. I hope that this introduction of the third-person observer approach has been of interest to you. What I've tried to do is to show you that what we need to do is to identify the construction rules of the observer who is building the theories first, because the errors, when we assume that everything is happening out there individually and independent of the observer, we tend to project observer effects into the world out there and therefore complicate it. Things would be simpler, easier, and more intuitively understood if we reformulate physics and therefore science altogether in a form that includes the observer and places observer effects into the observer system and external effects into the external system, and keeping those two separate the way they actually are. And I now would like to just open some general discussions, because I believe these effects happen everywhere, and we need to straighten out physics. And one question that I asked myself that might be the start point is, why did Einstein not introduce the observer in physics? Why did Einstein, probably fully knowing that his ideas were always generated within his imagination, and therefore his imagination himself, he being the third observer here, is always there in the background. Why did he eliminate that? And my answer is, Einstein did the best he could under the zeitgeist that was prevalent in the 1900s. At this time, all physics was formulated independent of the first-person observer. It was, even today, it's not allowed to introduce the first-person observer into physics. So at that time, it was total anathema. Nowadays, a lot of us acknowledge that the material of the first-person observer always supplies a preferred background frame. And this is a demonstrable, experimentally verified fact. As long as there are no forces or gradients, that exist in the observer's material, the speed of light is a constant and c squared, but it changes from the observer's material. If the observer's material is in a gravitational potential, the speed of light will depend upon the gravitational potential that the observer's material is. So the speed of light is not constant, it is simply constant within the observer's material within which all of these experiments actually happen. So let me open up the general discussion at this point. And Mark,
Okay.
back to you.
You want to unshare your screen, and then we can see everybody.
Let's see, how do I do that? New share.
Your cat caused quite a stir, I have to say.
Okay.
John Williamson.
Thanks for that, Wolf. I knew that was going to be very, very interesting indeed. And I share your sentiments on the observer being the center of the universe completely. But I want to simplify the observer down to a single elementary system. Take the observer down to a single elementary system. You've got three frames in the stuff you're talking about. You've got the stationary frame, the moving frame, and the observer observing both of those frames. But I think it's absolutely right that there is a conceptual bit missing in Einstein's thinking in terms of looking at relativity. And I would take that down to very close to what you're saying yourself as well in terms of the observer being important in these things. But I would say it in different words and in a different way. I just wanted to share some of those different words. I'd call every system, every elementary system, an observer. Give it a different name. Call it an actor, something that is capable of acting upon or being acted upon by other things. But those elementary systems are interacting systems, an interaction between themselves and the rest of the universe. And that interaction, when you're considering any particular frame, every single frame consists of something which is essentially in and of itself, both an elementary ruler and an elementary clock. So each observer has their own ruler and they have their own clock. They have their own system, which is their relative measure of space and time. And for the rest of the universe, as far as they're concerned, any dynamical processes formed by linear equations are going to be with respect to a derivative with respect to the process. Their dynamics is going to appear as a derivative in space and time with respect to their space and their time. And you have to do these reciprocally for everything, for every actor and for every interaction. And I think I talked about this a little bit at the end of one of the other talks in terms of some of the misconceptions that are happening at the heart of the quantum entanglement debate, where I think that exactly what you're saying in terms of thinking about the observer as being essential to the process is missing in terms of the conceptual debate which has been held in that field. And I think it's a very important brick that you've put into the wall of how these things have to be thought about and very beautifully presented. So thank you very much indeed for that. And I think I'll come back to this one, or I aim to come back to this one in a later Quisical talk as Lou and others have suggested should happen. So thank you for that, although I know you have more to say on the subject as well. So let me know if there is more that you'd like to say, and we'll make sure that happens first as well. But first and foremost, thank you. It was lovely. And I think there's a great deal of truth in what you've been saying.
Thank you. I think we're in almost total agreement. What for me is very important, there's one slide which I think is the most important, so I'll put this back up real quick and share that right now. Can I do it? Screen, whiteboard? Well, doesn't seem to work. Strange. Share. Okay, here we go. So this slide I consider to be the most important, because what I think you're saying and what I think I'm saying is that we live in the experience, which here is shown as this oval. That experience that we live in and from which classical physics and ultimately quantum physics has been derived it consists of two types of sensations. One generated from the input-output data stream of measurement. The second one produced internally from our model of what we think the world is about. These two things are combined, and this is the world that we actually live in, which means that the world we actually live in is model generated. And our difficulty is that we think that model generated internal world that we live in is the reality, when in fact the reality is that we are living in we're living in an activity, and this is a larger activity which produces it. I don't know how to explain this anymore, but if you look at just your television set, what we've been doing in physics is to look at the screen. And we've been looking at the screen and trying to build a physics out of what we see the relationships on the screen. If we step back and realize that the screen is part of a system that is producing the vision on the screen, we'll see that there's a bigger system, and we are a larger system within which the screen is being generated. And the real physics should be the larger system, and not just looking at the screen. I'll stop sharing that, but I don't know if that makes sense to, but that's the approach.
I think that kind of approach does make sense, but I would take it even further than you do and take the screen down to something which is a single elementary particle and the environment to the rest of the universe. So, sorry, the observer down to a single elementary particle and the screen to the rest of the universe. So we're all part of that process, which is the process of the interaction between whatever we are. And okay, we're a collection of particles. We're a bit more complicated than a single particle, but those particles are interacting in some way that cause us to create the world that we live in. But what's out there is the other half of all of that. Is the other part of all that. The interactions that we have with the universe, we are implicit. We are contained with and contain them within ourselves as a reflection, as a partial reflection in terms of what we comprehend, of course, but as a reflection nonetheless. Now, a single electron may comprehend a good deal less than the collection of electrons and protons, which we are, but nonetheless, that same elementary process is at play. That elementary process being the action, the actor acting on and being acted by the rest of the system in which it's embedded. So I agree with you as far as it goes, but I take it further down to elementary processes and elementary particles and the rest of the universe, up to the rest of the universe and down to the elementary particle.
Yeah, I mean, absolutely agree. I've tried to make the split at the anthropomorphic level, you know, that the rest of the universe and myself being two systems that interact. But the only way I know about the rest of the universe is to build within myself a model. I can't get out of myself. Absolutely. So the best I have of what the rest of the universe is like is stored in my model that I externalize from my head out into the book so that it can be shared. So now I have the whole thing together as I have to build better books.
You're right. I mean, that's the thing that struck me when you said it. You said the best model that an observer can build, but I immediately got the best model an observer can communicate.
Can communicate.
Then you have that difficulty of perhaps being able to share that whole thing, and then. But yes, I agree with you.
Right. But now the split, okay. Although I've been talking in terms of personal, the split is obviously that since any one of these elementary particles can be treated as an observer, you can split any elementary particle apart from the rest. And now you've got a observer versus the rest, and that gets into Peter's division, you know, which I think is very close to what I'm talking about, but not quite, and I'm trying to figure out how to get it together. So
it's all in the communication.
Okay. All right.
Looking at the screen, I've got Richard, Colin, and Lou. I've got no idea who was first, but let's take it in that order. So if we do Richard first. Richard, you're muted. You new to this?
Oh, all right.
Thank you for the talk. One of the extensions that I think would be very interesting would be to paraphrase Plato's version of the story, and instead of looking shadows on a cave, look at cathode ray tube images floating around on a screen. And the main reason for doing that is those of us watching you now have a good understanding of screens and probably a not very good understanding of what happens in a cave. So it would be an updating, and I think it would be helpful. Thank you.
Yeah, that's good.
Yeah, yes. I mean, this is, for me, there was sort of an epiphany when I added a book to basically Mark's drawing. I said to myself, well, what do these people in the cave do? And now Plato assumed that he could break the shackles of being in the cave, that he could walk outside and he would experience the reality in its full glory and so on and so forth. And he came back and he said, you know, you poor people in the cave, you know, you're stuck in here. You don't see the beauty reality of that world outside, which is a mathematical world. And I said, well, that's nonsense. He can't get outside of his cave any more than I can. So we're stuck. We're stuck building within our world, if you will. We're stuck having to build symbolic models. And our job is to improve the symbolic model, fully recognizing that it can never be equivalent to supposedly getting outside, which only quote unquote God can do. And I don't actually believe that's possible. But I think it's very important to realize that we are effectively the prisoners in the cave, and we are doing the best we can by externalizing our ideas of what is outside into symbols. And that the activity of creating the symbols and using the symbols is more fundamental than any of the symbols we can write. It's the activity of writing, reading, and using that is the activity that should be used as fundamental building blocks of our event-oriented world rather than object-oriented world. So I hope that, yeah.
Okay, so we've got Colin, then Lou, and then Nicola, and then John Torday. Okay, so Colin.
Okay, this is just a quick remark, actually. While Wolfgang and John were interacting a few minutes ago, I just thought, well, Wolfgang's being Plato and John's being Aristotle, and they're a quite different point of view. Wolfgang is definitely observer-centric, whereas Aristotle has an external reality. Wolfgang points out that we build the external reality from our internal, from this individual bubbles of consciousness. And there may not be any external reality. There may just be bubbles.
Okay.
Yeah, well, am I muted?
Yeah, no, you're fine.
No, you're there.
No. Okay. Yes, exactly. There may not be any external reality, but you can't live that way. I mean, we do something. We do something. So the best we do is we come up with some assumption. And, you know, what I kind of say is, you know, Kant already said that external world is an unknowable. So we got to leave it at that. But it's not unnameable. And therefore, being nameable we can construct what Wittgenstein calls use symbols. They have no experiential equivalent, but they're useful. And they're useful in operating our models. And we need to simply continue to improve our models. And my own, I would say, contribution is to say that as long as we do not fully appreciate the role of the observer in the process, we're going to project observer effects into the outside world and make that outside world more and more and more complicated. And I think that's what I'm seeing in physics and science in general today, is that we've made our model of the outside only world more complicated because we failed to understand to what extent the observer effect is actually the real cause of what it is that we're seeing. Anyway, yes, your point is well taken, and I think more fully understand. Let me give you an example, all of you an example, okay, about the screen and so on. Okay, if I am an astronomer and I do an experiment, what I see will be a dot on a screen or a dot on a photographic plate in the old days. That is the beginning of the projection internal to ourselves. It's a dot somewhere. It doesn't stop there. But now I, as the astronomer, intervene and I use that dot as an input to a mental process. The mental process develops a theory, and the next thing I say is, I think I'm seeing a star. I don't see a star. All I see is the dot. I have projected the idea of a star, and that is a complete theoretical creation. But when I walk around and talk, I'm always talking about, I see the moon, I see the stars, I see your face, you know, but that's not the process. What I'm seeing is the dot. I am then adding my own personal framework into the flow of information to create the explanation, and I talk in terms of explanations all the time. And I'm missing the idea that I'm constantly doing all this stuff. And it's the doing that's important, not the thing that's the result of the doing.
Okay. It seems to me, I mean, that it's like a Platonic pragmatism you're articulating. I just want to leave that hanging there, but that seems to me what it is. Lou, and then Nicola, John, and now John Williamson as well. So Lou.
Yeah, if you take this point of view, then you have to be very careful about what you regard as fundamental, because it's very easy for someone to say, well, I'll take an even deeper point of view and I will think of the elementary particles as the fundamental entities. But the elementary particles is a particular kind of model that you're taking, and you could take some other kind of model. And so if you're going to take this point of view, you have to realize that you are going all the way back to ground zero and asking what could you regard as elementary, and know that you don't have the answer to that. You don't have the answer to that, but you can find out what it is that you create. And what you create then can turn into other theories. And the final result of that is that you can become more open-minded about everything that we do, because you can assume, from your point of view, Wolfgang, that there isn't a single thing that is fixed. Nothing is fixed. No single thing that you care to name or put your finger on is any more fixed. And you only chose it to be fixed in order to keep on going and doing your science. But nevertheless, some things are repeatable, and we have to ask how they're repeatable. And you come back in that round to basic science again. But you have to come back to basic science without any prejudice whatsoever.
Absolutely, yeah, that's absolutely the case. However, now just to qualify that, I would say that when I listen to your discussion, I would say that you're at the same time you're stating something, and you're stating the thing in terms of something that you see. What I'm trying to say is that
Wait. What do you mean I'm stating something in terms of what I see?
well, I'd have to go back and rewind this whole discussion, but I think what you're saying is there's something out there, and
No, I'm not saying that there's something out there. I'm saying that you have experiences, and if you had no experiences, there would be nothing to talk about. And I'm saying that you're embedded in language because you are, and it's your birthright, and you have to understand that you have the freedom to speak, and to speak about what you speak, and to be critical of what you speak, and to doubt what you know. But beyond that, I don't say that what you see is there.
well, yeah, but
What you see is exactly in the same status as the Necker cube or any other optical illusion. It's a mixture of some things which can be verified by other means, and other things which are straight illusion produced by the system, whatever system that might be.
May I come in on that one? I think that there's something here which is very fundamental, more fundamental than the fundamental particles, and that is that the third observer can always be excluded. If you have a three-observer system, it could be that the third observer cannot observe that system. In fact, for elementary processes, it is always the case that the third observer is excluded. And an elementary process occurs between an actor and the thing which is acted upon, and nothing else. And that, for elementary photonic process, cannot be interrupted by anything else. It's from A to B. There is no C. So one can infer it as somebody looking at it from the outside if one sees a process which is associated with that, or which is measured by instruments, for example. But that connection is a one-to-one connection, which excludes external things if we're talking about a quantized emission and a quantized collapse at some other point. That's something which is not in principle interferable with by a third party at all, base of quantum encryption. And
well, yeah, then you make your third party into a theory.
You make your third party into a nothing, into something which is not connected with the process. So then the observer...
then you're only looking at it from the personal. That's fine, you can.
Well, you're making it up then because you're in your mind. But I think what you have to think about with an observer is what is observed and what is it observing in? What is it? What is it that observes, and what is it that it observes in?
Well, the whole universe divides into a part that observes and a part that is observed in the most elementary place.
Always, yes, that's right. So one has a system, but the observed part may also be a single part of the universe somewhere else. It could be another. It could be a star far away. You're looking at a star, or a galaxy far away, where you're looking at light coming from that particular galaxy. There's a connection between those 2 points, which is an intimate connection. So that's a binary thing. It's something which is not interruptible. Now you can develop systems that will, and I think this is a big mistake that's made in terms of not thinking about what is observing, what it is observing in. The whole system is that system for that event. When we're talking about an event.
Right, but notice that event creates an observer and an observed, both
it creates
at once.
An actor and an acted upon, and it also has intrinsic in it a process of time, because the actor is the thing that acts, and the acted upon is the thing that receives. So in that sense, the arrow of time goes from the actor to the acted upon. So it also
yes, but now look at what you've just done. Okay,
yes.
You've said, look out there. Here is the transmitter, and here's the receiver. Okay,
yes.
You've taken a third person's point of view in talking, right? And that third person point of view that you've taken is purely theoretical.
Yes, it's either theoretical or after the event. That's correct. Yes.
Which means that the transcendental, if you will, viewpoint that you have just taken is completely theoretical, that you've made up.
But he
And
could
that's
take it.
my point.
But
is that
Wolfgang, he could take it personally. He could say, "It is my observation. It is the observation that it happens to me." He doesn't have to take it as a third person.
It's really very much more than that, because if you look at, if in everyday things, you look at any object, if you didn't find it where it actually was, we wouldn't be here. You have to find the objects of the world where they actually are, and the brain has been evolved to do just that. Because if that didn't happen, then none of us would be here. It would be most inconvenient to say, look, there's the telephone, but it's not where you see it, it's somewhere else. You just cannot, I believe that Wolfgang has in many ways got it right. It could perhaps be expressed more simply, and I hope to tell you on Friday exactly how that might happen. But I think basically he's done a very good job of explaining that there is a third observer out there. If the third observer might just be the universe itself. You can't get the universe out of this, even if you are the receiver and something else is the transmitter.
Peter,
In the background is the universe, and the universe, as in the diagram of the eye looking at itself, is what has got to be somewhere in that picture.
Yeah, but the eye looking at itself is what I consider to be that phase-locked loop with the external world. There is now you are looking at the eye looking at itself, and from that point of view, you have suddenly taken a transcendental but only symbolic transcendental viewpoint. You have built a model. You've looked at a piece of paper with an eye looking at itself. And your viewpoint of that eye looking at itself is from
I won't say any more about it. I'd just like you to listen to my talk on Friday.
All right.
And I think you'll see that we're very close together.
Okay, I want to be fair to people who've been waiting a long time to talk. So Nicola has had her hand up raised, and then John. Nicola, you're muted.
I know. Thank you. Okay, so as some of you know, I'm really a member of Anpa because I'm interested in models more than physics. I'm interested in the mathematics more than physics. So I'm listening to what he's said in that way. And so I've been interested in, the idea of the first person observer, I think, is very important. And I very much liked it when you introduced the term the actor, John, and also interaction. And the thing is that in interaction, and also another term that's important is event, right? Rather than particles, events. So an event, one of the most important events, well, there are events between me and the universe, but there are events between me and other people, and there are events between people which are not, which may be what you're talking about, this one-to-one, John. But there is something. I'm kind of on, whether this has any resonance with anybody else here, I don't know. But there's a sense of throwing the baby out with the bathwater, of saying, well, it's all just models, and I don't agree with that. I mean, because that is this whole thing of like, it's the the essential of the meaningfulness of our lives and of life, of this amazing, beautiful reality universe in which we are. And respect for that needs to be, you know, any model, any way that we're thinking, for me, is recognizing a reality. It, you know, has to recognize that, has to have respect for this amazing beingness that we're in. So that's a rather muddled thing that I'm saying, but I'm just, that's all. But yes, I like the start of the first person observer, because I think that's very important to recognize where we are, but also that we are in, as you know, you were saying, Lou, we're embedded in language, and the language is a social phenomenon. So we have our own, you know, we are essentially social beings. Human beings are social beings. So, so I'm interested in embedding any physics or mathematics within the real, within consensus reality. So I mean, I see that we have just a number of different kinds of reality, and I'm interested in the way the different realities interact with each other. Yeah, and so I'm just throwing that out because I'll need to go very soon, actually. But yeah, okay.
John Torday.
Nicola, I think what you're talking about, at least in my parlance, is that we all recognize that there's something greater than ourselves. Mm-hmm. So with regard, Wolfgang, to great talk, I think I could superimpose my talk on yours in the sense that I think that your external realm is Bohm's implicate order, and we are the explicate. And so the transcendent part of this is that we know now that we evolved from the physical environment. We are the physical environment. And I maintain that if we were to map our physiology as a network and factor that out of our way of analyzing the cosmos, that we would be more in sync with it. We would not have the differential between the observer and the observed. They would be congruent. Comment?
Well, yes, of course. The key is to recognize that we are the observer, and that the observer actually creates the explanation for the sensations, which may or may not be the correct ones, even if there may not actually be a correct ones, because the cosmology that I've pointed out in, I think, the second or third slide, when you take the Platonic point of view, which means that the things you see around you are first off are sensations created inside your bigger self. When you take the Platonic point of view, the cosmology moves from the classic cosmology that there's this independent box out there with objects floating around and forces between them floating around. You take that cosmology and you replace it with the cosmology that you are inside your own cave attempting to rationalize the sensations that you receive from your sensors, attempting to rationalize it. And the only cosmology that's out there is interactions between other things that are in their own cave. So rather than the cosmology of the universe being a box with objects in it, it becomes an interacting set of individuals who have sensations, who are trying to explain the sensations, and the cosmology is an interaction of these individuals rather than a box with things in it. And therefore, the cosmology and the reality that I'm trying to impose out there is one of activity being the most important rather than the state. So we take state snapshots, but we tend to lose the activity that happens between the states, and I think that's the important thing that we have to concentrate on. What happens, the activity itself.
Yeah, but Plato and Aristotle those were abstractions, but in reality, we know that we're not abstract. We are integral with the physical environment. That's a given. And so that's why all of this, so we're always evolving in order to maintain equipoise with the cosmos. So naturally, we will evolve in tandem with the expanding universe. And that's not an abstraction, that is a reality.
I agree. I mean, in the world of this gentleman who became a slave in America, Kunta Kinte, he came from apparently near Gambia, and when his son was born, he took him immediately outside to the starlit sky, and he held it up and said, "Behold, this is the only thing greater than thyself." And that, so there's a very early recognition, even among people who had no science, but perhaps had a story history, and perhaps not even no writing, but they were aware that out there was something incredible, something so marvelous that it contained all of us.
Okay.
Everything else.
Well, I'd have to say that in my theory, what you are talking about is not out there. That out there is an internal effect.
Yeah, yes,
I
know that.
You have built that effect by growing. When you were a little kid, you had no idea of what that world is out there, but you built an internal representation. And
yeah. But I intend to show you that, in fact, although you build this internal memory or structure, which is your brain, mind, self, that in fact the only thing that gives it objectivity rather than subjectivity is the fact that all the things out there, you find them where they actually are. And so even in primitive peoples, when they looked up into the sky, they recognized, because they could even detect that the sky was moving. That's how they erected all these giant temples and things like that. And they needed to have this information because they were agricultural people. And the weather was the weather and what was out there was significant to their world. If they didn't have some angles on it, then they weren't going to survive. Okay. So what is out there is, I intend to show you, you actually do see, but you keep a replica of it in the form of a hologram memory in your brain.
So Peter, this is on Friday. This is your talk on Friday.
This is on Friday.
Can I just, because there are still people waiting to ask questions. So Roger, and then Lou. Oh, sorry, no, Roger, and then John Hyatt, and then Lou.
Hi, hello. Can you hear me?
Yes.
Okay, thank you. Thank you, Wolfgang, for giving such a good talk. The main point I take away from it is you're saying bring back the preferred frame, and ideally that is something that Einstein should have said, but didn't seem to. So it's suggestive that he didn't properly understand the theory, and which then suggested that he was not the main contributor to the theory, with the most likely candidate being that his wife was helping him write the theory. So that was the main point I was trying to make. And so what does he think of that?
Well, okay. There's been a lot of talk about Einstein and his wife and so on, and my guess is that it was a collaboration and she probably did not get the full credit that she should. Nevertheless, I'm saying that, as happens in many, many instances in science, the special relativity construction of an identification of the Lorentz transformations as being a ubiquitous part of our physics is due to the fact that when a coordinate frame is built, according to the instructions that Einstein proposed, the basic assumptions that he proposed, then we actually introduce errors. And in order to correct those errors and make our experiments and other construction things actually work, we have to correct those errors so that we have two errors. And the reason for those errors is that the observer has not been taken into account. Let me now propose to you that the entire ability to say something is where it is, which Peter was designing, the where is a completely observer effect. We don't know where anything is. We have sensors, and we interpret the sensor information in terms of an internal model, and the internal model gives us the where. We do not know where things are out there. It's one of the things that fundamentally we have to correct in physics. And you can see it all over the place where this happens. You know, for example, you can get rid of if I'm walking next to someone, and I've done this, you know, and now I speed up, I can make the person next to me have a kinetic energy. But the kinetic energy is an observer effect. I have moved, I, the observer, have moved, and I projected a kinetic energy into the thing out there. It's happening all over the place. We have to straighten out the fact that we are falsely projecting observer effects into the world out there. And I've tried to show that that constant error in our thinking is exemplified by special relativity. Special relativity is a correction imposed on an incorrect coordinate frame construction. Okay. And if we, and this was just an example of one thing. It happens in many, many, many places in science. And if we properly identify the role of the observer, we can eliminate those errors, and we come up with a simpler science that just makes a lot more sense.
Okay, so John Hyatt is next.
Yeah, I was just going to maybe observe that this is a disease of science, whereas the humanities always take account of the observer, and the observer's is never elided from the knowledge. But if we go back to Whitehead, where he said the concrete is the acting, and the abstract is that which acts, that seems to map on to what you're talking about. That was in Science and the Modern World. And basically that we're living in a world of events, and that in order to live in the world of events, which is incredibly complex, we actually hold multiple models of what's out there, or what we perceive to be out there, simultaneously. And we can actually flip fairly promiscuously between models for what we believe in order to just get by in the day-to-day.
Yeah, absolutely. We live in multiple models. We have multiple models. They're different. However, what I am proposing is that any model that you can generate must fit within the mental thought process. And the thought process needs to build some model because we cannot get outside of ourselves. Therefore, we must build a model inside of ourselves that gives us then the illusion of knowing something, the illusion that it's correct. And on top of that, correctness is a practical criteria. If it works, it's correct. If it doesn't work, we die.
Okay.
And we get around that by having kids, and they hopefully do things a little better, and so on and so forth. And that's the whole evolutionary process is now understood as an evolution of the model that we build inside ourselves, which we hope to get more and more correct.
Okay, we're going to stop at 7. Sorry, 7 here. Lou, very quickly, did you have another point?
Yes. We speak in metaphors. We talk about outside, but for those of us who are thinking as scientists, outside doesn't mean outside in the sense of existent outside. It means that entire range of possibilities that we might find new things, where something new might occur, how something new might occur, what we don't know. And that becomes, that settles into the metaphor of the outside. So in mathematics, if you're not a Platonist, you can talk about all that mathematics out there, but it's a metaphor. It's strictly a metaphor. You're talking about something that is being created and constructed, and so all this talk about it's not outside or there is no outside should be respected with it's all right to use the metaphors when you understand that they are metaphors.
Just to make a comment, I would say no, they are not metaphors, because the symbols themselves are use symbols. They actually are physical things that interact with each other to produce our activity that does go into the unknown, who knows, and produces
in some unknown
like.
formal system in which you live.
Yeah, right. But that's internal to me. And it's not a metaphor. It's not necessarily that these symbols are representative of something out there. These symbols simply interact with each other. And I've built this interaction business in order to calculate something. And what I calculate is my hand motion, the next thing I'm doing. And that's an internal activity. These are use symbols.
Please imagine that you were speaking to a poet.
Pardon?
Please imagine that the person you're speaking to is a poet, not a scientist. And you've just denied that he has metaphors? He has a different formal system than you do. And you have to respect that he has a different formal system than you do. He uses the same words, but he does them differently because he's running a different formal system than yours. And so does everyone.
If I'm talking to a poet, I think I am talking to a poet right now, because you're a poet that happens to use mathematics and other things in your poetry. That's true. However, I am also saying that some of these symbols are what Wittgenstein says are use symbols. They are not metaphors. They are not representative of something else. They are not suggestive of something else. They have an intrinsic relationship to other symbols in order to do a calculation.
Well, of course, we're saying the same thing. We're saying the same thing. You could take the notion of the outside world literally, or you can understand that you also take it figuratively as that place that I explore, where I explore.
Okay,
so a physicist wishes to explore outside world, a mathematician wishes to explore a certain symbolic world. They understand that they're related to one another.
If I build a calculation system like a calculator or some kind, an old-fashioned types where I turn the crank, somewhere inside that system I have a little wheel. The wheel turns. I would say that that wheel itself is not a metaphor. It is a use symbol of something that works with the other little wheels in order to produce something. They are not necessarily metaphors. They are tangible things that do something on their own to produce a calculation. So in that sense, a use symbol is not a metaphor.
Okay. I said.
Well, yeah. I wanted to ask us to not argue over the meanings of words so much, but apparently I created more arguments. So I nolo contendere.
I suspect we could go on for another hour, which we're not going to do. Well, thank you so much. This has been such a philosophically penetrating presentation and discussion that it's very, very interesting, very close to my own interests as well. So no, it's really fascinating. So thank you. Tomorrow, Sahu, what are you going to talk about?
Yeah, hi. Thank you so much for giving me a space to present some work that we've been doing over the summer. I mean, of course, I wanted to ask Lou permission to, if that's okay, if I share some of just a brief overview over Appendix 9 of Laws of Form, which was a joint effort. It's going to be in the Laws of Form 50th anniversary publication, and we've been working on it for a couple of months now, and it's been a journey. And I would be more than happy to share all the explorations that have come about, all the discussions that we've been having over the last few months. I want to invite Jim too, if he's available.
Oh yeah, no, get him to come along. That'd be great.
Yes, and I'm really excited for the Q&A session too. It's a bit of an intense journey, so I would suggest a lot of coffee and, you know, like a pen and paper, you know, if you have it for tomorrow, because it's going to be a big historical introduction, and then going into a reading of Appendix 9 and two small theorems that came up that we proved just a month ago or something. So. Yeah.
Okay, well, I'm really looking forward to it, and I'm very sorry Charry couldn't do the presentation tomorrow, but I'm so delighted that we found a slot for Sahu. That's really good. So okay, so that's tomorrow. I'm also going to tomorrow. I'll probably send it around the Anpa list. Just decide on the rules for the plenary on Friday. Try and work out how many. I mean, we're going to have about 25 people conservatively, possibly. I mean, so that's actually not very long each. But anyway, let's see what we can do anyway. Okay, thank you very much, everybody, and see you tomorrow. Okay, bye-bye.
Bye.